Now let's move on to a more dynamic phase of flight, the climb. How do the forces change when an airplane needs to gain altitude? We will focus on a constant angle climb, which is a controlled ascent where the aircraft maintains a steady climb angle. This is important for fuel efficiency, predictable performance, and ensuring safety clearance of terrains and obstacles. There are two critical climb speed pilots use. The first is the best angle of climb, or Vx. This gives the greatest altitude gain over the shortest horizontal distance and is used for clearing obstacles right after takeoff. The second is the best rate of climb, or Vy. This provides maximum altitude gain in the shortest amount of time. This is a standard climb used to get to a cruising altitude efficiently. Other types of climbs include the cruise climb, which is a more gradual ascent at higher air speeds, and the step climbing. As you can see in this flight profile diagram, long-haul flights will climb to a certain altitude, burn off fuel, become lighter, and then step up to a higher, more efficient altitude. To climb, the forces must be unbalanced. Specifically, thrust must be greater than drag. This excess thrust is what allows the aircraft to ascend. To generate more lift, the pilot increases the angle of attack, but this also increases drag, so it's a careful balancing act of energy management, converting kinetic energy from the engine thrust into potential energy or attitude. Mastering different climb techniques is crucial for obstacle avoidance in mountainous area, getting above bad weather, and optimizing fuel consumption. Essentially, different flight scenarios require different climb strategies, and understanding the physics behind them allows for optimal and safe performance. Let's break down the forces in a climb. As this diagram from NASA shows, things are now tilted. Lift is always perpendicular to the flight path. The red is flight path, this is lift. And the drag is parallel to flight path. Drag. Weight, however, always acts straight down towards the center of Earth. Because our flight path is inclined at a climb angle C, we call this climb angle C. The weight vector now has two components, one that directly opposes lift and one that acts in the same direction as drag, effectively trying to pull the airplane back down the slope. This is why we need thrust to be greater than drag to climb. This slide summarizes the direction of all the forces we discussed. To simplify our analysis, we can define a term called excess thrust, which is simply the thrust minus drag. This is the net force along the flight path available for climbing. We can then rewrite our vertical and horizontal force equation using this term. Furthermore, the small climb angle, which we can make approximations where lift is nearly equal to weight, and the horizontal force is simply our excess thrust. Modern airliners with powerful engines can generate very high excess thrust. This allows them to use steep climb angle for rapid altitude gain. A key benefit this is that it allows them to get high above populated area around airports quickly, which helps reduce the noise impact on the ground.